Today we're going to see this example that you see on the screen, and our objective is going to be how to obtain the system of equations from this bond graph model. So the idea here is the very first thing is we have to create the bond graph, and then we have to do the equations. As we have seen in previous lectures, I have presented that I think there's a set of steps that you can do to generate the bond graph model, and that's what I would like to see. We apply those steps. We're not going to concentrate on those as we did in other examples in prior to this, but we are going to concentrate on how we obtain the equations once the bond graph model is done, and that would be the emphasis today. So let's disappear from here. Okay, so the first step that we do to draw the bond graph model is to use a one junction um, for every distinct velocity. So I am going to draw the bond graph sort of on the system itself. See how we like this. This is going to be the velocity v1 of this. This would be the velocity that this has up. Okay, this over here, I'm going to use a one junction here, which is the velocity v sub 2. And this is representing the velocity that goes up. And then on the ground, I'm just going to put the velocity of the ground as well here. So we're going to do the bond graph model right on the system. A second step was to attach the elements that see those velocities. Then obviously in here we have an I element like that with value m1, and we also have the weight of this, which is modeled as a source of effort with value m1g. Okay, then in here we have the same thing. This would be an I element with value m sub 2 and a source element with the SE, yeah, like that, with SE. Okay, let's just do it better here. I'm just trying to draw it a little more clean here so that we don't get confused. So there we go. This is going to be with value m sub 2 g. And then over here we have the value of the ground, which would be a source of flow with some input, whatever the input from the velocity is, like this. So in between these two, you see, if we assume that this would not first, this will follow, then it follows that you can model the difference between these two velocities using zero junctions. So if you have it like this, perhaps we go from the bottom would be better. This minus this would yield like this. This minus this velocity, this would be b of the ground minus b sub 2. And this one over here, you will have would be, this would be b sub 2 minus b sub 1. Another one junction. And then over here, you have the elements that see these relative velocities, which is this R element, and then you also have a C element, the spring. And the same thing is, no, we don't have a C element over here. Hold on for a second. This one only the spring, so no, we don't have, this is all we have. And then in here we have, from here we have these two elements. See the difference between this and that, and so we need to put that in here, and this is C element, and the R element. This is our case of 1. This is going to be B1. And you see what has happened right now. We basically have finished. We could enter this into CAMG and do the simulation. But the objective right now was not that. It is to obtain the equations. So what I'm going to do now to be able to do that is I need to finish this, putting the causal marks in here so that everything, and the numbers. So if you assign integral form, and then of course we assign it first also to the sources, yeah, then once this is into here, this has to be like that. And then you put this one in integral form. We know that this has to be like this. This is okay. Okay, so let's put this one in here because when you put this in integral form, this has to be like this. When you have two like this forces this to be like that because of the one flow, and then this too, this will have to be in integral form for the C element. So once these two are like that, it forces this to be like this because only one effort input to the 0 and one float over here. And then this is going to be like this. And that's, we're done. The only thing that we are left is to number this thing, and then we don't really have a set way of numbering this. 5 and 6 and 7, as long as we number all of them, we are fine. 9, 10, 11. And then you have 12, and 13. Okay, so we have totally the model complete, and now we need to obtain the equations from this. So what I would do is I'm gonna go here and choose this. I am going to say the first one, let's call it equations using the individual constitutive laws. Yeah, let's to make it clear. It says equations using individual constitutive equations. So what I would do is I'll write two equations for each, one for the effort, one for the flow. What is E1? E1 is equal to, like in this case, E sub 2. See, look at the causal mark. And this, of course, it could be simplified, but we also know that f1 is equal to f sub 2. So this, you could do this like that, always equals to this, or this, like that. See? So you could simplify this if we want to, but I think it's not worth it right now because there's only one element in there. But let's go to 2. What is E2? E2 is determined by E sub 3. So let's just do E sub 3. What's F sub 2? F sub 2, okay. So F sub 2, I would say in this case, we have F1 equals to F2. F2 in here is equal to F sub 5 plus F sub 3. And then we have to move to 5 and 3. Well, F, so we go to number 4. So E4 is equal to 1 over C sub 4 times P sub 4, like that. This is the integral form of the C element. What is F sub 4? Is equal to F sub 3. And what is E sub 4? E sub 4 is 1 over C. Okay, so we are on E sub 4. E sub 4, E sub 4 right here is 1 over C sub 4 times Q sub 4, yeah? And also we know that the Q sub 4 dt is equal to F sub 4, right? This is the first differential equation coming out from this element. We have 3 differential equations, no, 4. 1, 2, 3, 4. The I's and C's will produce those.
Is that the same E sub 4 that's up top?
Where?
From the E sub 4 that you just wrote, the 1 over C4 P4?
This is E sub 4.
No, and then E sub 4 and then 2.
This is 4, right?
Yeah, I'm saying
This is
in the equation.
this is a V E2. I believe this is no, I think I meant to write E sub 3 and no. The answer is no, because this actually, this E sub 4 should be this. So let's just make that correction right now, so that just this one right here. Now we're fine. What we don't have is 3, and we should do that. We should put the E sub 3 and F sub 3. So why don't we make it, we'll fill it in here. In this case, E sub 3 is determined by the sum of the one. So E sub 3 is equal to E sub 4. And F sub 3 is F2 minus F5. Yeah, so we have covered this, so we go to E sub 5 is equal to what? Is it also E3? Because it determined what E5 was. And F sub 5 is equal to F2 minus F3. And then there's the one more on this column and go to the right. E sub 6 and F sub 6. E sub 6, that's this one right here, is SE6. And what's F sub 6? Is F7. Yeah. So we're 6, so E sub 7 is what? 7 is E5 plus E6 minus E8. That's the E7. Um, this is dp sub 7 dt is equal to E sub 7. And F sub 7 is equal to 1 over I sub 7 times P sub 7. That's this second one, differential equation. Now we're going to go to E sub 8. E sub 8. Who caused E sub 8? This variable not on the side is F sub 4, E4. Or is, no, it's E9, excuse me, yeah. E sub 8 is equal to E9. And then what is F sub 8? F sub 8 is going to be equal to F sub 7. See, F sub 8 is either two things. Who caused F sub 8?
F sub 14.
Huh? Where is 14? So we have this minus this equals this, the flow sum. So F sub 8 is going to be F 9, no, F14 minus F9. Yeah. So this is F sub 8 now. Where are we? This would be is F sub 7. So E sub 9 is E10 plus E11. And what is E sub 10? So is 1 over C sub 10 times Q10. And the derivative is dq10 dt dq10 dt is equal to F sub 10. So that's the, how many more bones we have? Only 4 more, right? Maybe we'll do it over here. I'll just put it like that so we don't get confused. and use my space efficiently here. But so Q10, now we're gonna say is E11 and F11. So E11 in this case is, where's number 11 on our bonds in here? Actually, this should have been 11 right here, right? We haven't gotten to those yet, right? Because there's no other 11. It should have been 11. Where is it? Oh, this one. Yeah. No, so we are fine. So F11, so E11 is gotta be R11 times F11. And F11 right here is F sub 4. Yeah, F11 is equal to F sub 9. Yeah, this one. And so we don't produce any more differential equations from the system. So that is, all right. Then we have F11, we have E sub 12. That is number 12. Or it's over here is SE12. And F sub 12 is F13. E13. That's in the integral form of the I element right there. So we need to write the equations accordingly. So this is F13 is equal to 1 over I13 P sub 13. So we have the 13 done. Now E13. In case E13 estamos. E13 is equal to E12 plus E14. Okay, E13, F13, E14 is E14. That's the last one here. It's E9. And F14 is what? F14 is F13. Okay. So these are the individual equations. So how can we use this to put them into the Cauchy form of the equations? There is a form. The Cauchy form implies that you use the individual constitutive equations to produce simple expressions in first order form. That's what it means. So in here, I would start with the derivatives. Make sure that we have 4 of them. If we don't have 4 of them, we're missing something. This is 1, 2, 3, and I don't think that I13 has the derivative. Like, yeah, right here. So this is one of the equations. F13 is equal to 1 over I13. But in here, we are missing one equation. This one in here, I'll just put it down here, is the